Hey guys, my name is Tensor. Today we're going to be starting our Introduction to Elixir tutorial series. This is a series that I've been looking forward to doing for a long time, and I know quite a few of you are interested in this series of tutorials as well. Now if you want to go ahead and install Elixir, you can go to the webpage elixir-lang.org/install, and on here are instructions for various operating systems and platforms. And if you just follow those instructions, you'll install both Elixir 1.8 and Erlang 20. Erlang is a development platform that was built primarily for scalable and reliable systems. It was created in the mid-80s by a company called Ericsson, which is a Swedish telecom company. And Erlang was created based on the necessity for the company to be able to handle thousands, if not millions, of different phone calls through their telephone switchboards in a way that these switchboards would be highly reliable, responsive, and scalable, and would be constantly available 24 hours a day, 7 days a week. If you consider what computers looked like in the mid to late 80s and the early 90s, most software was desktop-based, and the need for high availability was limited to specialized systems such as these telecom switchboards. Today, however, things have sort of changed. We've got the internet and the web, and most applications are driven and supported by some kind of server system that processes requests and crunches data and pushes the relevant information to many connected clients. And so this pattern, which was created inside of Erlang, is now extremely useful for web technology as well as embedded technologies. And this is kind of where Elixir comes in. So with Erlang, you have a syntax that's very similar to something like Prolog, and this makes it very unapproachable for the average programmer because the syntax is a bit foreign and a bit verbose. With Elixir, on the other hand, the syntax was written so that it would be more clean, and it looks more like something like Ruby. Beam, by the way, stands for Bogdan and Bjorg's Erlang Abstract Machine, and those are two of the scientists who invented this machine. You've got the Beam, which runs on one operating system thread, and the Beam has a bunch of schedulers inside of it. And these schedulers manage the processes, and when I mean processes, I'm not talking about operating system processes. Instead, I'm talking about a concurrency primitive inside of Erlang, which is called a process. And an Erlang or Elixir program can have literally millions of processes running all concurrently inside of the application. These schedulers take these open CPU cores and then they spread the actual execution of the program across these CPU cores in a very even and nice distributed manner. So by default, when you're writing Elixir code, everything is very opinionated and directed towards this kind of distributed and highly concurrent way of writing code. Now, as you can see here, Elixir and Erlang have a very similar compilation path. So Elixir goes through and it is converted to an Erlang abstract format, and then that format is converted to a core Erlang format, which is then converted into Beam virtual machine bytecode. More specifically, we have an initial parsing step which turns it into a large AST, which is just a big old tree with a bunch of information inside of it. And then the AST is added to a macro expansion piece, which takes all the macros that are inside of the AST and just expands them out, which gives us back this expanded AST. And then that AST is used to generate the bytecode. Now let's open up the interactive Elixir shell. So Elixir is a dynamic programming language, and that means that we can run the programming language directly on a REPL like this. I've got this one open inside of Emacs, but if you want to open it in a different environment, you can open it up in your command prompt, or you can use something like Sublime Text and the Sublime REPL plugin. To run interactive Elixir, you just type in IEX, and you'll get a little prompt like this. Now, the reason why I'm not running the shell inside of the command prompt like this is because on Windows, you don't get auto completion. So if I type in, say, enum period, and then I hit tab, it just gives us a tab. It doesn't tell me what functions are attached to the enum module. However, if I go into Emacs and I type in enum dot, there are tons of different functions here inside of this list, and I can choose from them and I can look at their documentation as well. Another way to access the tab autocompletion on Windows is to use the WERL flag on IEX. You get a little graphical user interface like this, and again, you also get tab autocompletion. Elixir is also a functional programming language, and this is something that I definitely want you guys to keep in mind as we proceed through this series. Every operation, every function, every block inside of Elixir is considered to be an expression, and the main idea behind expressions is that they always have a return statement. So everything you write in Elixir code will always return something. And that's something that I want you to keep in the back of your head as we go through this code. Now, because Elixir is a dynamic programming language, we don't need to explicitly declare the types for a variable, and we actually don't need to explicitly declare that we're creating a variable. The type of the variable is going to be determined by the data that is contained inside of it at that moment. So if I make a variable x and I set it equal to, say, 10, then x is now variable of type integer because it references the value of 10. This is what's called variable binding inside of Elixir. The equals operator is actually used for pattern matching inside of Elixir, and we'll talk more about that when we actually get to pattern matching in this series. But now you can think of it like you're binding the value of 10 to the variable x. And of course, I can perform operations on the variable as I would with the actual values. Now, Elixir uses the Erlang type system. The type system itself is pretty simple, and there are a lot of really easy to understand primitives, and we'll go over those right now. So we have integers, as we've seen. I put in x equals 10, but I can just type in something like 3, or I can type in something like 5, and it's defined as an integer. I can also write integers in a hexadecimal format, and the system will automatically convert that hexadecimal format into a readable format. So I've typed in 0xFF, and I've got back 255. We've also got float values, 3.14159, which are the first digits of pi. As you notice here, when I divided the integer 10 by the integer 2, we got back 5.0. That's because the normal division operator, the /, is an operator that will take the integers and convert them into a float by default. As far as floats go, we can use scientific notation. So I can write 3.0e -2, and this will evaluate out to 0.03. And of course, we've got standard arithmetic operators as well. So I've got addition, I've got multiplication, we've got subtraction, and of course that will give us a negative number. And as we saw, we've also got division. Now, if I do want to divide two integers and get back an integer, I can use a function called div. And notice how I'm invoking this function. I'm just typing in div followed by the two arguments with a comma between them. So I don't have to put the parentheses in here, but I can if I want to. So I can just type div 5, 2 like this, and these are equivalent to one another. Along with div, we also have a remainder function called rem. So the remainder of 5 divided by 2 is 1. When you're dealing with fairly large numbers in Elixir, you can also use underscores where you would normally use commas. So here I've got 1,000,000, and I've got an underscore every 3 zeros. When I hit enter, you can see it just gives us back a normal 1,000,000. And this is pretty nice syntactic sugar. We can also use extremely large numbers inside of Elixir. So here I've got some ludicrously large numbers which I'm adding together, and then we get back the result of this addition. Now, if you're worried about memory size, the memory is done automatically. So an integer will take up as much space as is needed to accommodate the number, and with a float, we'll either have a float that's 32-bit in size or 64-bit in size, depending on the build architecture of the virtual machine. Now let's talk about atoms. So atoms are literal named constants, and they're similar to symbols in Ruby or enumerations that you'd find in a language like C or C++. Atoms are constants which start with a colon character and are followed by a combination of alphanumeric symbols and or underscore characters. And this is an atom here. If you want to put a space in an atom, you can also use double quotes. As long as I start with a colon like this, and then I put double quotes, anything between it will be a valid atom. So even something like this is a valid atom in this case. Now the atom itself consists of two pieces. There's the actual text, and then there's a value. The atom text is whatever you put after the colon character, and at runtime this text is kept inside of a structure called the atom table. The value is the data that goes into the variable, and it's merely a reference to the atom table. And this is exactly why atoms are used for named constants, because they're both efficient in memory and in performance. So I can go ahead and bind a variable to an atom, and the variable var, which I just created, doesn't contain the entire text of the atom, but only a reference to the atom table. Therefore, the memory consumption of this variable is fairly low, and of course the code is still pretty readable. Another way to write an atom is to use an uppercase character, and this is what's called an alias. So here I've created an alias called a module, and of course as you can see here we're not using the colon at the start, instead we're just using an uppercase character. Now notice when I write this actually is equivalent to this. So colon elixir dot a module. And as you can see here, when I actually go and type this in, we get back our a module alias. So when you use an alias, the compiler will implicitly add the elixir dot prefix to its text, and then it will insert an atom there. So of course I can also do a comparison between these two. And when I type a module equals elixir.a_module, we get back true because they are the same values. Aliases are pretty useful because you can use them to rename existing module names. So I can say alias IO, which is the input-output module, as myIO. And now I can invoke any functions that are attached to the module IO with myIO. So myIO puts, and then I can type in a string, hello. And that will then print out hello to the console and then come back with an atom of OK. Aliases are the way that the code actually resolves modules inside of Elixir. And we'll talk more about this when we actually look at modules. Elixir also has Boolean values. So we have the value true and then the value false. Both of these values are actually atoms. So true is the true atom, and false is also the false atom. This true and this false are just a bit of syntactic sugar over these two atom structures. And because we have Booleans, we also have logical operators. So we have an AND operator. Then I can write true or false, which is a logical OR operator. I can use not, which is a logical negation operator, which takes the Boolean value and then inverts it. Along with Booleans, we also have another special atom called nil. And nil is like null in other programming languages. So nil can be written like this, or it can be written like that. So much like other mainstream languages, the atoms nil and false are treated as falsy values, whereas everything else is treated as a truthy value. So for instance, if I use a if statement, I can say if 10 do, and then I can say print out the string true, and then I have to put an end here. And you can see this comes back and it does print out true because 10 is truthy. And on the other hand, if I put in nil, and I put io_puts true, and then I put end, you can see here we don't have the printout. Instead, we just get back nil, because nil is a falsy value. So nil can be treated like false. And this idea of truthiness can be used in Elixir's short circuit operators. We've got OR, which are these double pipes, and essentially all this is really doing is it's saying, alright, nil is false, then false is false, and then the first value that we get to that's true, which is 4, is what we return. So this goes here, here, and then it doesn't have to evaluate the last part of this expression because it finds 4 and then it just automatically returns. Then down here we have AND, which are these two AND signs. So we're just saying true and 5. And then we have the negation operator, which is just the exclamation point. And I'm just saying not 5, which gives us back false. Now if we go back to AND real quick, and I type in, say, nil and 5, it returns the first false value. So in the first statement, because both are true, we get back the last item in the expression. And then in the second version, because the first item is false, we get back that false value. So if I write it like we wrote the OR expression up here, it goes true, true, and then false, return. And then it doesn't have to evaluate the last part of the expression. Now let's start to talk about collections inside of Elixir. So first let's look at what are called tuples or tuples. Tuples are something like untyped structures or records, and they are most often used to group a fixed number of elements together. So here I've created a variable called cat, and I've set it equal to the string Jasper, which is the name of the cat, and then the age 12, which is an integer. We can extract the values from the tuple using the elem function. So here I want to get the age value from our tuple. So I can say age equals element cat comma 1. And because tuples are 0th indexed, we have our name first. So if I recall cat, the name is 0. So here we're getting the first index, which is 12. And so 12 gets bound to age. Now if I want to, I can modify an element inside of a tuple by using a function called put_element. So here I'm typing in put elem cat comma 1 comma 13. And so we're replacing the 12 with 13 in a new tuple. Now notice that if I recall back the value of cat, we still get back the value of 12 inside of the tuple. So this doesn't actually modify the tuple data structure. Instead, what it does is it creates a new one with the string Jasper as the 0th index and then the integer 13 as the first index. This is important because all data structures inside of Elixir, so there's no way you can do an in-memory modification of a value inside of Elixir, and that's a very important concept to keep in mind. I can, of course, say cat equal put elem cat comma 1 comma 23, and all we've really done here is reassigned the variable cat to our new tuple. If we look at how this is represented in memory, it makes a bit more sense. So say we have a tuple with 3 values, a, b, and c. They are represented in memory as a, b, and c. And then when we create a new tuple, say we remove b and we put in a value d, it references the old a value, then it has its new d value, and then it references the old c value. B gets set up for a garbage collection, and then the rest of the references get pushed over to the new tuple. And so this is how it's efficient for Elixir to use exclusively immutable data. Now, if we want a dynamic sized collection, we can use a list instead of a tuple. So tuples are fixed sized, whereas lists are dynamic size. So here I've created a list with 1, 2, 3, and 4 inside of it. Now, while lists for the most part act like arrays, they are actually singly linked lists inside of Elixir. And so most operations that we can do on lists generally have a linear time complexity associated with them. And this of course includes functions like length, which gets the length of the list. We can get elements out of lists using a enum et function. So the module enum.et, and then we pass in numbers, and then pass in the index that we want. And again, lists are 0th index, so it goes 0, 1, 2, 3. If I put in a index that doesn't exist in the list, say 5, then we'll get back the value nil. You can also use the in syntactic sugar. So I can say 3 in numbers, and this will give us back true because 3 does exist inside of the list numbers. However, if I go 5 in numbers, because it's not inside of our numbers list, we get back false. Like with our tuples, we can also create new lists, and here I'm using list.replaceAt, passing in our list numbers, then saying I want to replace the 0th index value with a 12. Again, you must remember that we're not actually mutating the data here. We can also insert values into a list. So here notice I want to insert into the 3rd index the value of 13. So now we get back a list of size 5. If I want to insert the value at the end of the list, I can use -1 for the index. Another thing to keep in mind is that we have a concatenation operator. It's just 2 plus symbols, and we can concatenate lists with this operator. And this gives us back a list of 1, 2, 3, 4, and 5. Lists inside of Elixir are actually defined recursively. The lists can be represented using the pair head, tails, where the head is the first element in the list, and then the tail points to the rest of the list. If you're familiar with a language like Lisp, this is a concept called cons cells, and we can use the cons operator to actually deconstruct a list like this. So here I put in a value head, and then I'm using the cons operator, which is just a single pipe like this, and then I'm putting in the value of tails, and I'm setting it equal to a list of 1 through 7. And now when I recall back the value head, I'm going to get back 1, and then when I recall the value of tails, I'm going to get back 2 through 7. Our list here, 1 through 7, can be represented using the cons operator like this. And when we resolve this expression, you'll see that we just get back our list of 1 through 7. On a list, we can just continue to recursively do this until we come to an empty list. We can use the HD function, which is the head function. This strips the head off of the list, and then we have the TL function, which is the tail function, which strips the tail off of the list. These two operators are actually of a constant time complexity, which means it doesn't matter what the size of the list is, they will always take the same amount of time to execute. We can use this recursive definition to our advantage. So say I create a list with 15 Adam and true inside of it and then set it equal to a variable. I can then go ahead and say add a new element to the head of the list by putting it in a list like this, saying Adams, for instance, and then using the cons operator and then putting in our a list. And then this will give us a new list where Adams is the first value in our list. In Elixir, we also have maps or hash maps. So we can create an empty map by using a % symbol and then curly braces. And maps are essentially collections of key value pairs. Maps in Elixir tend to have two main usages. So they're used to create dynamically sized key value structures, but they can also be used to manage simple records. You can create a map like this. So I'm creating a map where each of the keys is being squared. And then if I want to recall a value, I can put the key into the variable using square brackets. So up here I'm recalling the value that's connected to the key 1, and then I'm recalling the value that's connected to the key 2. We can also use a function called map.get, pass in the map and then the key that we want to get. So I want to get the value for 3, and we get back 9. If we put in a key that doesn't exist in the map, then we just get back nil. Now, as I mentioned before, we can use maps for structured data types, and we can do this by using atoms. So as you can see here, I can say cat equals name of cat, is Jasper as a string, and then the age of the cat is 12. And I'm just using atoms here, the atom name, but notice that the colon is inverted. This is just a syntactic sugar that makes it easier to write the map. So instead of having to use the arrows between the keys and the values, we can just write an atom. And now I can access the values using the key by typing in the name of the variable dot and then followed by the atom name. So cat.name will give us back the string Jasper, and then cat.age will give us back 12. We can also, of course, fetch the values like we were doing before with square brackets. So I can just type in cat and then pass in the atom name, and this will give us back the string Jasper. For those of you who are used to object-oriented programming or even functional programming, this will look very similar to records or to very basic data objects. Now, say we just want to change one of the values inside of a map, we can use the cons operator like we did with our list. And then I'm saying I want to change the age by putting in the age atom and then putting in the value that I want to change it to. And of course, this isn't actually modifying our old map, it's just creating a new one. And of course, we can go and get older cat.age and we get back 15 now. Now let's quickly talk about binaries and bit strings. Binaries and bit strings are a little bit unique to Elixir. They're something that you're not usually going to find in other languages as a primitive. We can create a binary, which is just a chunk of bytes, by using these angle brackets like this, and this is just a 3-byte binary. If I put in, say, 256, we'll get back 0. And that's because this is all based on bytes. So the byte value can't be higher than 255 in this case by default. And so we get back 0 if we put in 256. And if we put in 257, we get back 1, and so on and so forth. If we want our byte size to be different than the default, we can change it using double colon. So I can say 256 with a 16-bit representation, and this will give us back a bit string of 2 bytes, and we can do the same for multi-bit bit strings. We can also concatenate bit strings using angle brackets like this. So 1, 2 is now concatenated with 3, 4, and that gives us 1 through 4 inside of a bit string. And there are a lot of things that we can do with these binaries, but this is just a very surface level look at them for now. This kind of leads us into strings. Now in Elixir, we don't actually have a dedicated string type. We represent strings using a binary or a list type. So we can create a string using double quotes. The result is printed as a string, but underneath it's represented as a binary. So it's just represented as a consecutive sequence of bytes. Strings in Elixir have interpolation, and you can do that using a pound and then curly brackets like this. And all that really does is it takes the return of an expression and then puts it directly into the string. So add together 3 plus 4, and it gives us back add together 7. Normal escaping works inside of Elixir as well. In Elixir, you've also got what are called sigils, which you can create with a NA symbol and an S, and then parentheses, and then this just converts into a double quoted string. Anything inside of it is put into a string, which again is a binary. Sigils are fairly useful if you want to include quotes inside of a string. So for instance, if I want to put double quotes inside of this string, I can just go ahead and do it like this. If you use this sigil though, you can't actually use string interpolation. So if I use this sigil and then I try to use the string interpolation from up here, it'll just print out the expression that's in the string interpolation rather than resolving it. We can also concatenate strings together using the same operator that we use to concatenate the binaries together. Now, using single quotes gives us what are called character lists. So here I've put in ABC inside of a character list. And if I want to represent it as an actual list, I can go 65, 66, 67, and that gives us back the single quoted ABC. So the character list is essentially just a list of integers where each element represents a single character. And as you can see, the runtime doesn't actually distinguish between a list of integers and the actual character list. Again, with the single quotes, we have string interpolation, and we've also got sigils. So instead of an NEAS, we've got NEAC to create a character list, and then that gives us a sigil. And all the rules apply that we mentioned before to character lists as they do to strings. The only difference, though, is that there's a module for strings called string, and there are various functions in this module that we can use. So like string to char list can take a string and convert it into a character list. But if I was to put a character list into this function, we would actually get back an error because the character list is represented differently than a double-quoted string. And generally, you would actually use the double-quoted string in most cases, though there are some fairly cool cases for the character lists as well. Alright guys, well that's it for today's tutorial. If you like this tutorial, feel free to subscribe and like. If you have any questions or comments, feel free to leave them in the comment box below. And if you dislike this tutorial, then by all means downvote it as much as you like. Have a good night.